And all this cell, right, will compare with the hydrogen gas cell. Okay, for metal cell, just need a piece of metal. Okay, deep inside the solutions. The metal, let's say it's called metal M. Okay, it doesn't matter about what it is. Okay, so just put a piece of metal M there. It's an electrode itself. Okay, then the solutions, right, must contain your M ion of 1 molarity, 1 mole per gm cube. It is a standard metal cell. Okay, a gas cell, it is a inverted funnel. Okay, and then deep inside the water, so you have some gas. Okay, try to dissolve into the water. And the gas is in 1 atmospheric pressure. Okay, and then the solution inside must already have 1 mole of your gas, let's say H plus, 1 molarity, okay, of the ion. Okay, you don't care about the partner. Okay, the partner, for example, if you're H plus, you can put a nitrate ion there also can. Doesn't matter. Okay, but you must have 1 molarity, that is 1 mole per H plus. Okay, ion cell, right? ion cell is let's say you talk about a redox between Fe2 and Fe3. Okay, a redox between Fe2 and Fe3. So what you need to put is that you need to make sure you pour 1 molarity, okay, of Fe2 and 1 molarity of Fe3. Okay, and put a graphite electrode inside, or diamond platinum electrode inside. That is a standard standard cell. Okay, so all these things, right, is to check the negativeness you can have. Okay, why is there a negativeness? Is that the idea is that if you have something to oxidize or reduce to something, for example, in this case is metal versus metal ion. Okay, so in the beginning you put a piece of metal. In the beginning you put 1 molarity of M plus. Okay, so if both of them would not like to go over the other side, I should read no electron or 0 potential at the metal piece there. So if I put equal amount, but some of the metal dissolve in M plus of course try to solidify become metal also, but if there's an overall urge of dissolving M plus, okay, then I will have excess electron in this piece of metal. I will have a negativeness develop.
Okay. M plus, you have a lot of M plus.
you have equal amount M plus and M.
But I thought your M plus wouldn't go back.
No, remember before this we talk about if you just dip a piece of metal inside water, there's no ion. Okay, the metal will try to dissolve, become M plus. Okay, and you keep dissolving until equilibrium is reached. Then with this amount, we have a corresponding amount of electron remain in the metal. That means, right, all matter in the world, when they touch another phase, right, it will try to go into another phase, from a metal phase to aqueous phase. Okay, it will try to cause phase, and it will always achieve a dynamic equilibrium. Okay, and have something about 2块年糕. Okay. They try to ditch one another, they stick together. Okay? So when somebody they ditch one another at the time, they're very happy, they say high five at the time. Okay? So it's best they get back together. Okay? The kind of things that when you touch another phase, right, you have a tendency to go to another phase. And then a dynamic equilibrium will reach. And then there is electron here. But this is not fair. Not fair because this one totally have no M. Okay, so when this dissolves, doesn't mean that M love to go to M plus. Okay, so this is why we need to be fair. Then we start to talk about the relative urge of the state of M or M plus in the oxygen state, the urge of going to some oxygen state. Okay, by measuring how much of a negative potential here. So in this case, right, the metal natures like to become solution form than the metal. By giving some fair comparison, okay, you will have some. If you have some negative. Okay, if you have some negative, means that some M is overall dissolved in M plus.
So how you measure that?
So you take to a voltmeter, you check negative. Okay, because
the solution itself has to have M.
Say again.
The solution itself has to have M plus really.
Yeah. Okay. So this must have already have 1 mole per gm cube M plus. On the other hand, right?
What if this is a higher concentration than the equilibrium.
Then it's not called a standard cell. You can do that, but it's not a standard cell. Okay, the different concentration will make your potential here varies, really. Okay, it will change one. But we talk about the nature of these elements.
Standard is always one more.
Yeah, they standardize everything and they compare with one another. Okay, all compared with hydrogen cell.
What if 1 mole is really more than the equilibrium?
Yeah, so what if this is already too concentrated? The idea is that it's nothing to do with too concentrated, but it says that one molarity, if one molarity, the urge of the metal under one molarity will love to stick to become metal instead of the metal dissolve, right?
Oh.
Okay. In this case, the metal plus will try to become M, you will take the electron. So then the original electron M here will got lesser. So then your voltmeter will be positive instead.
Oh, so the positive negative doesn't matter.
Yeah, so this one, because you have both, you can allow both positive and negative reading. Okay, so to tell you the positions that you can have and how to measure it, use this E naught value. Okay, E naught value. Okay. So same thing. This is a gas between gas and ion. So the gas love to become ion. Okay, this one will have a lot of electron. If the ion love to become gas, this one will have lesser electrons, so it will be more positive. And then this is Fe2, Fe3 or ion shell. Okay? It's actually a graphite electrode, just put 2,1 molarity ion inside. If there is a net off of F21 to become F3, Fe2 become Fe3, then this graphite electrode will read some excess electron. If there's a net off of Fe3 want to be Fe2, right? Then the graphite electrode will lose some electron, so it become positive. Okay?
Oh.
If none of them want to be equal stable about Fe2, Fe3, they don't want to become one another, then you shouldn't read anything.
You only can use same atoms on, is it?
No, all these things, right, is the experimental way to construct your half equation. The definite half equation says that if I have this ion want to become that, another ion of another oxidation state, right? So it certainly will still be the same thing. Hydrogen plus. Then you have the hydrogen plus delta E naught how much? Okay? So we talk about when I have one elements want to change oxidation state. What's the urge or what's the ease kind of things?
So this is a setup to measure the amount of E naught increase or decrease.
You're right,
for
okay.
half equation, then we add both, then we
Yes.
find
And
out how much.
the half equation is already compared to hydrogen.
Usually the value is already given, is already known.
Yep, it's in the table. Okay.
So we use the value, then we say how we go about finding.
Yep. Yep, you're right. Okay, so but where does it come from? This is the one. Okay, 3 cells, metal cell, gas cell, and ion cell. Okay, so in this 3 cell, right, we have to link up your cell. To link up your cell will have an electrode out, metal electrode, graphite electrode, you have an electrode out. Okay, and then they will tag along with voltmeter, and then they will tag along with hydrogen standard gas cell, hydrogen cell. Okay. And then put a soft bridge inside here. Okay. Actually, you have soft bridge, no soft bridge doesn't matter because voltmeter doesn't allow current to go through really in physics. Okay, but chemistry people will just say keep flow. Okay, actually it cannot flow. Okay, so voltmeter actually read the potential difference. Okay, and the potential difference will tell you the E naught value. So if this one, right, think about this. Okay, if I have 2 cells, no need to care about hydrogen cell. If this one love to go to ion more than this one love to go to ion, okay, which one will be more negative in the electrode there?
Okay, which one?
If you have cell number 1, cell number 2, the ease of dissolving into ion, let's say they are both metal cell, this one dissolve more than this one dissolve. Which one do you think is more negative? Yeah, this is more negative, right? So you put a light bulb there instead of a voltmeter. Okay, this soft bridge. Okay. Then what will happen? The negative electron will flow in this way. Okay.
This is to measure what?
Oh, this is actually a battery cell.
Just to test, is it?
So that the current flow in this way, the light
Not
bulb
to
flow.
measure anything.
Is to measure the this is to make a cell.
If it's a voltmeter there, then what is it to? What does it? Is it?
It will
what
meet
is
the
measuring?
difference in potential of the 2 cells. that will
Can
give you
use
the value in the half equation.
But the half equation.
Yeah, that's how they find the value in the half equations there. The value. Okay, they put one hydrogen cell this side, they put one another cell this side. Okay?
The balance.
Yeah. So if you use a lemon, use a lemon, eating lemon, very sour lemon, plug a paper clip here, okay, and then plug a coin, let's say a coin of $1 coin.
But if it's the same lemon then.
Same lemon, okay, plug a lemon dollar coin, plug the same lemon there, and you put a light bulb here.
Why would there be a difference?
The light bulb will glow. Okay, it will work. Okay, why is that so? Because these two are different metal.
Oh, okay.
Metal will exit metal. When metal will exit, metal will form. Sorry.
$1 coin.
Paper clip and $1 coin. The color is different type, totally different metal already. Okay, so when the wave will exit, right, it will become an ion. Okay, so it is about a metal become an ion, metal become an ion. If the urge of this metal become ion is stronger than this metal become ion,
So it creates a flow.
yeah, so the electron will flow this, or the current flow there. Okay, so this is actually how it works when have a competition about the urge of forming ion. Okay, so the idea is that when they have a system, let's say, so this is how you find the E0 value. So how do we use the E0 value? Normally is to find the cell, overall cells delta E, or whether the reaction is feasible or not. Okay. So when they say I give you I want to see, I have a zinc and copper. I want to make a cell. Okay. So what is your delta E and how will the thing flow? Okay. So
will dissolve more.
yeah. Okay. Yeah, because we know last time. Okay, so let's don't care about zinc. We talk about iron and lead. It's not so familiar, right? It is true. Okay, so if you have a cell set up in this way.
First,
sorry.
iron first.
Well, cow. Remember everything. Okay. Tin.
Yeah, tin.
Titanium.
Iron first.
Okay. Okay. Can pretend that you don't know. Okay. Anyway, so the idea is this: when you put it here now, when you have a voltmeter and you have a salt bridge here, now you will have all kind of combinations. Okay, because you have Fe, let's say 3 plus. Interesting. 3 plus or 2 plus, they make a difference. Fe and Sn and Sn2 plus. Okay, so the idea is that whether this become this or this become this, the force this become this, okay? Now when this one try to dissolve, okay, without iron ring, okay, this one will not dissolve. Okay, because if when this one dissolve more, this electron will go over, and this one is it cannot dissolve. Instead, that when this become electron rich, this one stick back to here. So the stronger one, right, will choose to flow. Okay, the weaker one will be forced to flow against its nature sometimes. Okay, so what happens is that you have Fe become Fe3 plus, and you have Sn2 plus back to Sn.
Then there'll be extra of 1 electron.
Yeah, of course. Okay, you balance the electron by yourself. So this is 3 electrons. This is actually 2 electrons. So this time 3, this time so 2, 2, and 3, 3. Okay, you got to write this right. Okay, but it doesn't matter. Okay, what happens is that what one will say that iron will become this, and this become that. Okay, and that's how you. So what is the resultant battery? What will you read from voltmeter? Okay, choose this delta E plus this delta E. Add together. Okay, and delta E don't care about the 2, 3. Doesn't matter. It's talk about 1. Okay, so just add the 2 numbers. Is your cells
The bigger the delta E, then
the bigger the delta E,
Lighter.
the more feasible it is, the brighter the light it is. Okay, if the delta E is the addition of delta E, right? If it's less than 0, like delta H like that. If less than 0 means that this reaction is not feasible. It's not feasible. Okay, so things like this, they will say that can this Fe3 plus, okay, this is can this Fe3 plus H3 please undergo reduce. Oxidize H2O. This is ridiculous. Okay, can the Fe3 plus oxidize H2O? Okay, then you talk about Fe3 plus become Fe how much? Fe3 plus become Fe2 plus how much? Okay, because it is possible to come here to come here. Okay, and when this get reduced, H2O got to get oxidized. How H2O get oxidized?
H2O2.
H2O2 is the oxidations.
It will be H2O2.
O2 minus O. No, H2O2 is a reduction. Gain oxygens, right?
Gain oxygen is an oxidation.
Yeah, but how come minus 2 become minus 1? This is a minus 2 oxygens, right? And then become H2O2 is actually minus 1 oxygen. Right? Is it a reduction? Yeah, it's a reduction, right? Okay, so you can see. Okay. So let's try to see, can it be, can it reduce, can it oxidize chloride at the chlorine? Okay. Can it oxidize the chloride at the chlorine?
The
Fe3
iron.
plus, yeah, the iron 3 plus. Then you check the iron 3 plus to iron how much.
Then you put iron
And then you
chlorine
check,
outside.
take iron 3 plus to iron 2 plus how much. See which one is bigger. Take the bigger one. Okay, then you see Cl minus becomes Cl2 how much. And then add it up, see whether it's bigger than 0. Choose the biggest one, add this one. Okay.
So for the setup will be one side iron, one side chlorine.
We don't set up in this way, okay? So maybe this is to check the potential. Okay, but now we already have the value of potentials. So how can we deduce that this substance can reduce this substance can oxidize this or not? Or when something can be reduced or oxidized, meet that guy, right? This will get oxidized or reduced.
So some of them their potential is negative.
Yep. But the idea is that this is negative, this is more negative, right? You add up the time, may give you some positive things if you flip it. Okay? So
You negative and negative will confirm be negative.
not really. The way you write negative, right? Let's say this example. The Fe3 plus to Fe2 plus is plus 0.77. Fe3 plus to Fe, right, is minus 0.4. So the strongest one, right, is actually to Fe2 plus, so 0.77. So you choose 0.77.
Plus that of Cl minus.
Okay. Yep. Cl minus back to Cl. Do you see any? Cl here. Now this Cl to Cl minus is 1.36. So Cl minus to Cl is minus 1.36.
Oh. No, but 2Cl minus this one is.
Yeah, but you don't care. Okay.
Okay.
You don't care. Okay. This is the this is.
So
You don't care one actually. This because it's not per mole of electron per mole anything. This one. This is under standard conditions.
Okay.
What's your delta E? Okay, so you add this up. Okay, my 0.77. That's the best you can. Minus 1.36, right? It's still negative, right?
Not feasible.
Yeah. So that means it's not feasible. That's how they get reduced. Okay. Careful something about vanadium. Okay, you see a V there in the very end there. The V there, right, have many oxygens there. V. No, just V. V have 2, 3, 4, 5, 6, 7 state. Okay. So when they keep going to the next state, right, you just keep adding up the number. See, I can oxidize it until what? Which state? Okay. They can keep oxidizing.
Until it becomes negative.
Yeah, until it becomes like negative means the last step is still okay.
Okay.
Then that's what it ends. Okay, so that's how we use about the E0 value. Okay, but that's not for calculations. Really, just to tell you whether it's feasible or not feasible. Simply add it. Okay. For the last piece about electrochem calculations, right? It's just a Faraday constant, right?
You convert it to how much
Yeah.
the current.
Yeah, just like that. So, for example, they say under electrolysis of, let's say, HCl, okay, HCl, then copper electrode, interesting, okay, then they say battery, and they put let's say positive, negative this way. They say they say after let's say 3 ampere of current for let's say 10 seconds, okay, how much volume or gram of things produced, okay, or missing. What will happen? Okay, so now if the positive idea is to get the electron up, right? Okay, so when you get the electron up, right, this is either the metal dissolved or it right? So the copper, this is let's say platinum, okay. So the copper, right, it will dissolve instead. So in this case, copper become copper 2 plus 2 electrons. Okay, for this case. So the Cl minus, right, or versus the OH minus will not come into here and get discharged. Okay, so in this size, right, is H plus versus the H plus. So certainly they only have H plus. So H plus 2 electrons give you H2. Okay, so it's balanced. So you can say 2H plus Cu in overall equations, but you don't have to do this actually. Okay, so this is the overall reaction in whole circuit there. So the copper will dissolve and H plus will come out. So in order to answer this, 3 ampere for 10 seconds. Amount of charge is equal to current times time. So this is 3 ampere times 10 seconds. So actually it's 30 coulomb. Okay. Primary constant tells you that 96500 coulomb for every 1 mole of electrons. Okay, so therefore, number of mole of electron flow is equal to 30 over 96500. Okay.
Then you find this value, then you
wait. This is number of mole of electrons. Right. Okay. So number of mole electrons, you will come back to this thing.
the full equation first, right?
This one cannot help you. You need electrons, so use a half equation. Okay. If they're unbalanced, only balance it. This is why I said you don't need this.
Oh.
Stick to this. So if you have so many more of electrons, number of mole of copper dissolved is actually half of it. Okay, so half this value, you get a number of mole of copper dissolved. And time mR, you know how many gram of your copper dissolved.
The other half is what is being used up.
Yeah, you're right.
How about if they are not?
No, it's not half. Half is because the electron to copper is 2 to 1 ratio.
Oh, okay.
Okay, so this is number more electron. So number more electron divided by 2, you get number more copper. So this is copper dissolved. So time mR, you get the mass of the copper. Okay, on the other hand, in here, you know 2 electrons give you 1 hydrogen gas. So divided by 2 again, you get number of more hydrogens, then times 24, you get the volume of hydrogen gas come out. Okay. It's just how you use the 96500 coulomb. Okay? No anything tricky. This one, so don't worry about it. Okay, so next week, Wednesday?
Yeah.
Actually, Wednesday you guys will be free or
Sometimes
sometimes cannot.
Why not?
I don't know, but like some extra stuff pop out or something.
I think born.
Yeah, but can you try to shake away the extra pop-up things? Quite hard to reschedule this place because